When conversational AI exceeds its processing budget, the interaction doesn't degrade smoothly. It stalls, the illusion breaks, and the user experiences a dead pause. To maintain a fluid, human-like dialogue, we are operating under a non-negotiable processing budget, under 800 milliseconds per interaction. Hitting this number is relatively simple on a local development machine or a single server. A single processing loop can handle the transcription, inference, and text-to-speech synthesis without breaking a sweat. But physical distance introduces immediate latency. Fiber optic cables are bound by the speed of light. If your server is in Virginia and your user is in Sydney, network traversal alone will consume a massive fraction of your 800 millisecond budget before a single line of code executes. Even if the user is right next door, a single server architecture remains incredibly fragile. Sudden spikes in traffic will overwhelm the CPU, and if the system is juggling asynchronous tasks, like database writes, internal traffic jams will inevitably stall the primary audio stream. You cannot code your way out of physical distance, and you cannot optimize an application to absorb infinite traffic. To protect that 800 millisecond window on a global scale, the application code itself is insufficient. We have to enforce the latency constraints physically, using dedicated infrastructure components. Achieving reliable sub-800 millisecond streaming is a structural routing and system decoupling problem. The first objective is to build an edge layer that provides a single server abstraction. External clients should see one stable address, completely isolated from the complexity of your internal network topology. The standard approach relies on domain name system routing. You attach multiple server IP addresses to a single domain name, and the DNS hands those out to users one by one in a round-robin fashion. The issue is that DNS is entirely blind. It lacks health monitoring capabilities. If a server goes offline, DNS doesn't know. Because of time-to-live caching, the system will continue routing users to that dead server's IP address for minutes or even hours until the cache expires, resulting in hard downtime. To actively manage global traffic, we require Global Server Load Balancing, or GSLB. This diagram illustrates active traffic management in action. GSLB evaluates the user's geographic location, current data center CPU load, and network response times. Here, a Tokyo user is routed to a healthy, localized server in Seoul, bypassing a congested node in Los Angeles entirely. Once the user reaches the correct regional boundary, GSLB hands the connection off to a localized Layer 4 or Layer 7 load balancer. This component instantly fans the traffic out across a cluster of healthy parallel instances. By actively evaluating hardware health and physical proximity in real time, GSLB guarantees high availability and preserves the latency budget before the connection ever reaches your application layer. Once the user reaches the application layer, they cannot be allowed to communicate directly with highly specific, isolated internal microservices. Direct external access forces every single microservice to independently verify user authentication and handle security protocols. This introduces massive processing redundancy. This diagram shows the API gateway pattern. We channel all external traffic into a single API composition layer that acts as an absolute system choke point. This gateway executes three primary security functions before any data touches the internal network. It terminates TLS encryption, authenticates the user, and enforces rate limiting to block DDoS attacks. The critical rule here is that no application business logic belongs in the gateway. It must be strictly focused on routing and security. To prevent this choke point from becoming a single point of failure, you deploy multiple gateway instances behind the previous load balancer. In the context of our AI streaming platform, the gateway's specific job is to accept incoming HTTP requests, upgrade them to persistent WebSockets, and blindly route them directly to the orchestrator layer.
Functioning as a dumb, highly secure firewall, the API gateway absorbs the entire security overhead, allowing the internal microservices to dedicate 100% of their CPU to processing audio speed. Inside the network boundary, we face a major architectural tension, balancing the need for real-time synchronous speeds against the need for a scalable, decoupled system. The core real-time path, from the orchestrator to the speech-to-text streamer, must operate via direct, synchronous gRPC calls. This unbroken link is the only way to meet the 800 millisecond threshold. This diagram illustrates the necessary split. The top half is that strictly synchronous path. But an active session also generates off-path tasks, like billing and analytics. If the system pauses to execute a slow database write for a billing record, the synchronous audio loop breaks. We resolve this by inserting a message broker, like Kafka or SQS, into the architecture. The broker acts as an asynchronous buffer between the orchestrator and all off-path tasks. When sudden traffic spikes hit the system, the broker absorbs the surge. The queue fills up, but the downstream billing and analytics services continue draining it at their own steady pace, completely shielded from the overload. This introduces strict fault tolerance. If an analytics server crashes, the broker simply holds the messages safely in the queue until the service is restored. No data is lost, and the live stream is never interrupted. The broker utilizes a publish-subscribe routing model. A single event from the orchestrator, like the completion of a conversational turn, can be published once and simultaneously fanned out independent billing, analytics, and notification consumers. But because queues intentionally delay data to smooth out spikes, message brokers are strictly forbidden from operating inside the primary audio path. Applying this to our architecture, transcript logs are immediately offloaded to the analytics queue as fire and forget events. The generation of usage and billing records follows the exact same path. By physically bifurcating the synchronous real-time loop from these asynchronous business tasks, system bloat is entirely neutralized. Shifting our focus back out to the user's browser, we need to separate the dynamic WebSocket audio stream from the static configuration interface these are clicks through. To handle those static elements without taxing our core architecture, we deploy a content delivery network. This diagram outlines how a CDN operates. It physically caches static assets, HTML, JavaScript, and CSS files, on edge servers located at points of presence directly in the user's region. By skipping the long-haul transit to your primary data center, a CDN can reduce a 3200 millisecond page load down to mere milliseconds. We configure this using a poll strategy. The CDN automatically fetches the static content from your origin server upon request and caches it locally based on a strict time-to-live expiration. It is critical to note that the dynamic, bidirectional WebSocket streams powering the AI audio cannot be cached. They must bypass the CDN infrastructure entirely to reach the API gateway. Offloading the front-end interface to a CDN keeps the web app instantly responsive globally, preserving your primary server's compute bandwidth exclusively for the demanding AI audio stream. This diagram shows the completed global architecture. Static requests pull instantly from the CDN, while dynamic connections pass through the GSLB and regional load balancers. Traffic hits the API gateway firewall, entering the internal network, where it splits into the real-time gRPC loop and the asynchronous message queue. The internal topology is now highly available, perfectly decoupled, and completely shielded from external clients.
Theoretical application latency is irrelevant if the routing edge misdirects a user or forces them to wait on a long-haul network connection. The GSLB handles the geography. The API gateway absorbs security processing. The message broker buffers business logic, and the CDN offloads static interfaces. Global scale is not achieved by building faster individual servers. It is achieved by engineering infrastructure that strictly physically enforces your systemic constraints.